Okay, now we're going to do some examples out of section 8.1 and 9.2. Suppose we want to find the distribution of the sampling process for the sample mean, and that the underlying population has a mean of 57 and a standard deviation of 8, and that we're using samples of size 25. How do we find the distribution of the sample mean? Well, remember that the sampling process gives me estimates of the population mean. So the more samples I use, the closer I should get in on that population mean. So the average of the averages should work out to be the same as the population. So mu sub x bar will be the same thing as mu, which gives me 57. The standard deviation should also be related to the variability in the population. And we have the relationship that the standard deviation for the sampling process is the standard deviation for the population over the square root of n. In this case, that gives us a value of 1.6. What if I were to change the sample size to n equals 64? Well, nothing happens to the mean of the sampling distribution. It should still be the same thing as the mean of the population. However, because I increase the sample size, I will end up decreasing the size of the standard deviation of that sampling process. I will still take sigma over the square root of n, which now gives me a sample or a standard deviation for the sampling process of 1. So to come up with the distribution of the sampling process for the sample mean, mu sub x bar will always be the same thing as the population mean mu, and sigma sub x bar will always equal the standard deviation for the population divided by the square root of the sample size. So now let's look at an example where we want to come up with a 95% confidence interval. So let's suppose that we had the following information. The sample average was 41.8, the sample standard deviation was 9.6, and n is 36. And we want to find a 95% confidence interval for the population mean mu. Well, remember the formula that we have. The interval has a lower bound and an upper bound. It's given by x bar minus t times s over the square root of n. The upper bound is x bar plus t times s over the square root of n. And the t value comes from looking at the sample size as well as our level of confidence. How does the sample size relate to the t value? Well, the t distribution has a number of degrees of freedom. The degrees of freedom is always equal to the sample size minus 1. So in this case, we have 35 degrees of freedom, 36 minus 1. The other aspect of the t distribution, when we're going to look things up in the table, is knowing what column for us to look in. Well, with a 95% confidence interval, that means I'm getting the middle 95%. So that means there's going to be 2.5% left over in each tail. So I know that I'm going to look in the 35 row for the t distribution and in the 0.025 column. If I do that, I get the .35 row and the 0.025 column. I see that I get a t-value of 2.03. So I know I'm going to go 2.03 steps away from the mean, from the sample mean on each side. So I know I'm going to go 2.03 steps on each side of the sample mean. So I would take the sample mean of 41.8. I would subtract off 2.03 steps. The step size, remember, is S over the square root of n, so that's 9.6 over square root of 36, which gives me a lower bound of 38.552. The upper bound, I would add on 2.03 steps. Again, the step size is S over the square root of n, which gives me 45.048. So I have a 95% confidence interval of between 38.552 to 45.048. Again, remember that the confidence lies in the methodology that I'm using. I'm 95% confident that my method will capture that mean. The true population mean is either in that interval or it's not. So I can just talk about how confident I am that I've captured that interval. What if I wanted a 90% confidence interval? What would change? Well, nothing changes except the t-value. If I want the 90% confidence interval, I'm looking at the middle 90%. So I would have 5% on each side. So I would use the 5% column. If I want the 99% confidence interval, that would put a half of a percent in each tail. So I'd use the 0.005 column. Again, whatever the confidence level is, I'm going to take that away from 1. That's going to be the amount of the amount of area under the two tails combined. So I'm going to cut that in half to get the area under one tail, and that then tells me the column I'm going to look in. All of your problems on confidence intervals will work just like this example, and you will use the t-distribution to calculate those.